Hello, we are Master Robotics and we are going to show you the project for the subject mobile and articulated robots. The members of the group are Oscar Avila, Guillermo Castillo, Bolivar Núñez, and Steven Silva. So robots nowadays is mostly a common thing depending on the country. But till today, a lot of packages and solvers, really good tools have been developed in order to build and design robots. For example, there is one of the most known tools, which is MATLAB, which has a lot of packages and plugins that can be used in order to design robots and to test them. And there is also ROS, which basically does the same thing, but is a little bit more, a lot more, let's say, related to the actual design of robots and simulations. So till today, there have been a lot of problems, or there are a lot of problems that can be solved with designing robots. And the advantages that it gives is that developing a robot in order to solve a problem makes it a lot more reliable. It can also gives us more efficiency, because most of the work that is solved is made by people, and then implementing robots can make it a lot more efficient and without having any problems. But in order to do this, of course, the robot must be really well designed. And as a problem that we have seen in the industry is the arranging of packages. There are a lot of warehouses that certain, let's say, companies have, in which packages must be arranged in a certain way or be put in certain categories or areas. And years ago, this used to be done by people, but there could be some, let's say, mistakes in which the packages were not put in the categories that were wanted, or maybe there could be drop, and problems, specific problems that could be made in while repositioning the packages. So for a solution, we have proposed to make a mobile base with a robotic arm above it. And for this solution, we have been inspired by one of the solutions, or let's say by one of the already designed robots, which is the Jackal from ClearPath Robotics, as you can see in the right image, in which it is a rover with 4 wheels and an articulated robotic arm above it. Till today, there are a lot of solutions that have been made in order to repositioning packages and transporting them, like the one from Amazon Robotics. But in this case, we have proposed to put a robotic arm which could give a lot more of mobility, which will give a lot more of handling about the packages, since it will have a gripper. This solution could be destined, it could be related to any place which has warehouse, like UPS, even Amazon itself, or any company that will need to reposition and categorize packages.
Hello, my name is Bolivar, and I'm going to talk about the robotic arm. The robotic arm was developed. We developed the model of the robotic arm that will be mounted on the mobile robot. This was made in Inventor and consists of 7 links, of which one is the base. We have 5 links of rotation: the first, second, third, number 4, number 5, and only have one link that is the translations. This one, translation movement. For example, here that is the rotational. The same for these links, that is rotations. So I'm going to explain the direct kinematic that we use for the robotic arm. For that, we use the representation of Dynavik Hattenberg. The Nevin-Hartenberg is a systematic procedure to describe the kinematic structure of an articulate chain made up of joints with only 1 degree of freedom. For this, each joint is assigned to a local reference system, followed by a certain rules. The rule number 1 says joints are numbered from 1 to n, so we have to number a letter to the base. This is 1, this is 2, 3, 4, 5, and 6. We have 6 joints. Later, the direction of the z-axis goes in the same direction as the rotation axis of the joint. But we have to number starting at 0. So in the joint 1, the Z0 go up because we have rotation on this side, clockwise. For the next joint, it go outside of the plane because turn on this side. So using the system of right-handed, we select that the C1 axis go outside the plane. And the same for the next joint. Later, number 3, the direction of x-axis depends on if the C1 and the C1 less 1 axis are not parallel, the direction of C1 must go in the direction of the right-hand system from C1 less 1 to C1 to Ci. Number 3, the direction of the x-axis depends on if the Ci and Ci less 1 axis are not parallel, the direction of the xi must go in the direction of the right-hand system from Ci less 1 to Ci to Ci. For example, on the joint 1 and joint 2, the C1, the C0 go up and the C1 go outside the plane. So using the system right-handed, the direction of the x1 have to go on this direction. And we use the direction of the 0 at the same side to make easier the mathematical operation. On the joint 3 and the joint 2, we can look about the C1 and the C2 go at the same direction and both are parallel. So the direction of the x2 go at the same direction of the x1. But if the direction of the C are different, we use the direction of the x2 opposite to the x1. And we continue with the next reference system. But later, if the Ci and the Ci less 1 axes are parallel, the direction of Ci must go at the same direction of the C1 less 1. So in that case that I just explained that, if the axes of C are parallel, so we use the same direction for x2 like the x1. Later, number 4, the direction of y is done in such a way that the system of right hand. So, for example, we just define the direction of the axis C1 and the x1. So we use the system of right hand to know where is the direction of the y axis. In that case, it go up for the joint 2, and the same for the next referral systems for each joint. And finally, we have to apply the rotation or displacement arrows to each joint. For example, on the joint 1, joint 2, we have a rotational movement. So we use this one. And for example, 1, 2, 3, 4. On the joint number 4, we use displacement, translational movement. And that's all because all of the joints use a rotational movement. For example, here, number 5, 4, 3, number 2. No, only the 4, 2, and 1 and 0. Later, we have to make the array of the Navier-Stokes that includes the param of theta, the param of d, a, and alpha. For each join, we have 6 joins. So 1, 2, 3, 4, 5, and 6. The number 0 is the if or standard reference system for all the robotic arm. So theta is the angle between the CO and C1 axis using the direction of the XO. For that, we have to use the right-hand system. For example, between C1, in that case, it depends of theta 1. So use the theta 1. The param D is the distance between the both reference system. In that case, for example, the first reference system and the old reference system have a D1 distance. But on this case, because we are starting, we use the distance between the starting base to the starting reference system number 1. But the next, we use the same distance, for example, the number between the system reference, for example, the reference system number 4 and number 5, we have a D6 distance. So we use, for example, here, D6 distance that is less 50 millimeters. For D1, the distance is 326.713. Yeah. Okay, but in the joint number 4, in the reference system number 4, here the number between the number 4 and number 3, we have a D4 system plus 208 because the distance on this side is 208 millimeters. But if the links move forward, we have a D4. We have to add the distance that the link moves. Later, for example, the A parameter. The A parameter indicates the distance between the C1 and the CO axis. Indicate the distance between the C1 and CO axis. But the distance A needs to be perpendicular to C1 and C0, CO, how you can see on this part. Another example is between the axis 2 and the axis between the axis C2 and the axis C1. That is A2. Between the axis 2 and the axis 3, you have A3, and the same for the next link. And in the axis A1, we have 91.8 millimeters. How you can look here. And the parameter alpha indicates the angle between the axis of C. For example, for the first reference system, we use the C0 axis and the C1 axis using the direction of the X1 axis with the right-handed system reference. So in that case, we have 90 degrees. 90 degrees. Later, as system reference number 2, both axes of C are parallel, so we don't have any move or rotational move. So in that case, the angle is 0 for the system reference system. For the reference system number 3, the angle between the C2 to C3 using the X3 direction with the right-hand system, we have 90 degrees. And the same for the next reference systems to complete the table. Later, this is an example of using the array of the Navier-Stokes. If I introduce or incorporate the value of theta theta 1, theta 2, theta 3, and the h params of the array, we can obtain the position x, y, and z of the robotic arm. This position of the reference system number 6. In this case, we use the position and all angles and distance in 0. So we have this result that is the home position of the robotic arm. So we are going to use this array of the Neville-Hartenberg to we are going to incorporate it into a function that will use it to determine the final position of the robotic arm. For this, a simulation of the mechanism was carried out in MATLAB using the multi-body simulator, where the model made in Inventor could be exported. This tool automatically creates and converts each constraint made in the assembly into the reference frames, rotational reference frames, rotationals or translational transfer, and the solid object of each links. So however, this reference system and transfer were modified to establish a correct movement of the mechanism of the robotic arm in order to establish a home position. So in that case, this is our home position. Later, to make the correct control of the robotic arm, we use the tool of Inventor. We use the tool App Designer of the MATLAB. So how you can see here, we made it and create the fusion using the array of the Neville-Hartenberg. For that, the design includes the sliders where you can change the position of the rope to make a move in the joint of the robotic arm. And using the array of the Neville-Hartenberg to define the final position of the robotic arm. So this is the fusion that includes for each reference system, we have six matrix and obtain the final position for X, Y, and Z. And this is the callbacks to extract the value of each slider. So we are going to run this App Designer to make a simulation, to start the simulation. For that, I'm going to run in the O position. This is the O position. So if I want to move near 90 degrees, so how you can see 90 degrees. So for example, if I want to move near 30 degrees, 36 degrees, and in the joint 2, 50 degrees, and in the joint 3, joint 2, joint 3, less 12 degrees, and move 160 millimeters for the joint number 4, the links number 4, and run. So how you can see here, this is the final position. The final position is on X, approximately 600 millimeters on X. In the axis of Y, 435.5 millimeters. And for axis Z, 1,127 millimeters of height. So this is for the direct kinematic. With the inverse kinematic, for the inverse kinematic, it was developed using trigonometry. However, due to the fact that it is a mechanism with redundant degrees of freedom, it multiplies the roots that are generated to reach an third final position. Obtain several results in the equation obtained. So, to simplify the equation of motion to the robotic arm, the restriction of the movement of link 3 and 4, that here the links, the base, link 1, 2, the link 3, and the link 4, was established or fixed grounded. which has a translational movement and rotational movement, respectively. Then before, a schematic of the simplified measurement of the robotic arm is weighted, and it is possible to determine which link contribute to the position of the X and Z axis. For the Z axis, the height of the base and the link 1 and 7 in this part, the 7 between the reference system number 4 and 5, we have a distance and height. So these measurements are fixed for every time are the same, no change. It's not change. And only the link and only the link 2, 3, and 4 contribute more to the position of the X and ZX. And only the link number 2, 3, and 4, link 2, 3, and 4, contribute more to the position of the X and Z axis. For that, we use the trigonometric operations and later incorporate into the inverse button action, in the action of the inverse button. However, to determine the position or the rotational movement of the robotic arm, we use the X and Y axis in order to determine the θ1 angle. In spite of them, to certain model rotations, there are still problems, which is why a ROS tool was used for the inverse kinematic. For example, we use here in the app designer on the inverse button incorporate the equation for the inverse kinematic. But when we use this equation to run the simulation, we continue having problems. For example, here the robotic arm doesn't move because the position or the restriction don't let it to move. We just need to find the correct positions in order to the system of the MATLAB tools will simulate it.
Now I am going to explain the inverse kinematics of the robotic arm in another aspect. Since the mathematical expressions that had to be made for the inverse kinematics of our robotic arm were really complex, we decided to implement the robotic arm in a software called MoveIt from ROS. And basically what this program lets us do is that it simplifies things to have every parameter that we would like to have, for example, the trajectory, velocities, and even the value of the joints more quickly without having to think about the mathematical expressions. So in this case, since the inverse kinematics of our robot was really complex, since we had a slider, we decided to implement it. And this MoveIt package for ROS has a service called Compute Kinematics, Inverse Kinematics, which let us give it the position that we want from one of the links. In this case, it will be the link new to the end effector and the orientation, and basically it responds with the values of the joints. This is a really good tool because it's actually faster and more, let's say, more precise, and we wouldn't have to waste so much time thinking about the mathematical expressions. So, for example, with this position that I have here for the X position, Y position, and Z position, and the orientation, I'm going to show you how to get the values of the joint. So, to do that, I have to run this code that I have already made, which calls the service and publishes to it the position, and what we get back is the values of every joint. For example, as you can see here, link 1, link 2, link 3, link 4. We have here the values of all of them. For example, for for link 5, which is the slider, we have that it should be minus 2.05. Let's try another one. Oh, sorry, it is minus 0.21 meters. So let's try another one. Let's see. And just as before, it gives us the values of the joints. In this case, for example, this link has been rotated a little bit more in order to have a higher C position. Also, apart from the inverse kinematics, we can also have the forward kinematics, and for that there is a service called Compute Forward Kinematics, which we have already coded so that we can get the response from it. And basically what it gets is the current position of the robot that you can see that is a little bit orange here, and get the final position of the robot. Basically, we get the value of the joints and get the final position of the near to the end effector. So I'm going to run it right now, see what we get. And as you can see, according to the values of the joints, the actual values of the joints, we can get the position near to the end effector. So with this tool, what we have been able to make was to get a more precise calculation of the forward kinematics and the inverse kinematics without having to think of the mathematical expressions. Also, this Move It tool lets us, for example, move the robot around and get the planned process so that the robot gets to that position. Let's see, for example, imagine I put the robot in these positions, and I can plan the trajectory of the robot to get to that position. Let's see, as you can see, it is already planning the trajectory. Let's make it, let me put it a little bit more down, for example there, so that it looks, yeah, that seems a bit better. And we can execute the trajectory. There, it is moving. This tool, since it does all these calculations, also can also give the velocities of the joints, which we have already showed in the final document that we are handling. So that's it for the Move It and inverse kinematics with ROS.
Okay, so for the differential robot, first a trajectory has to be established. We use this trajectory where in the x-axis we use 0.1 times t, and for the y-axis we use 2 times the sinus function of 0.1 times t. Then we had to establish a controller in order to move the differential robot in the trajectory that we wanted. So first we use this vector where all the components for the movement of the robot are defined. We have Al, R, theta, and the two angles were the two angular velocities. Then we took out the two velocities for the wheels, and then we had to define the matrix using all the components and using the rotation matrix. Finally, the matrix for the velocity was constructed and the trajectory could be established using all these equations in here. These equations right here were used in order to determine the error of the trajectory. In order to make the simulation for the differential robot, a program was written in MATLAB. Here we define the time for the simulation, and then we had to put the initial parameters in order to establish the controller for the robot. Here we put the trajectory we wanted the robot to follow with all its own parameters, and then we establish the controller using a for loop where we use the control law for differential robots. We also establish the matrix for the values of the gains, and also we had the Jacobian matrix. Finally, the positions for the robot were established in order to put them on the graph, and also we had to find the error for the positions. So when we hit the run button, so here we can see the robot following the trajectory. So when it arrives to the final place here, we can obtain the graph for the error. Oh, here we have the graphs for the velocity and the angular velocity, and here we have the graphs for the errors in the x-axis and the y-axis.
Hi, my name is Guillermo Castillo, and I'm going to talk about the analysis of results, conclusions, and recommendations that we have obtained for this project. So, for the analysis of results, according to the design that was made of the differential mobile robot with 4 wheels, together with the articulated arm that it carries, kinematic equations were obtained that will describe the movement of the two parts. On the part of the movement of the mobile base, mathematical relations were obtained to describe its movement as a function of speed, both for what will be the x and y axis with respect to the global system. Being a four-wheel robot, to make turns it must turn the front wheels like a car, so it is considered that there is a certain limitation to its movement with respect to turns, so that the angle of the front wheels has its limits. It was necessary to define the robot as having 4 wheels in order to have the necessary stability to support the movement of the robotic arm. In the event that the greatest amount of mobility for the mobile base is wanted, omnidirectional tasks will have to be considered. On the other hand, for the articulated arm, the method was used by the use of Dynabit-Hartenberg parameters. The direct kinematics of the robotic arm was obtained correctly, which was verified when simulated in MATLAB. Regarding the inverse kinematics, quite complex expressions were obtained since the robotic arm was defined with a slider-type joint. For this reason, certain limitations have to be assumed, such as the slider is static and certain angles are kept at 90 degrees, with which the equation for the inverse kinematics could be obtained satisfactorily. To obtain all the major degrees of freedom for the robot that was designed, and to do what is inverse kinematics, MOVEit was implemented with ROS, with which it was possible to obtain the value of all the joints for a specific position in the space of the M effector. Regarding the trajectory control, it can be observed that for the movement base, the velocity and error graphs were obtained for the linear and angular velocity. The graphs were shown to be quite smooth, even though the error does not converge to zero from an initial point, but is due to the initially specified path. In the case of the robotic arm, in the same way, the speeds were obtained that show a sharp increase in a certain position, which is possible that it refers to a singular point of the system, but the error shows to converge to zero at the end of the path that was defined. In the same way, given for the process carried out, the inverse kinematics was used with its limitations in the slider and certain angle. Their solution in ROS was also implemented to be able to observe the speed that each arm joint has, which proved to be more attached to reality and are more accurate. Finally, considering what is defined in the navigation architecture, the use of a LiDAR is enough to have a decent navigation. This is capable of following both navigation and mapping of a space so that the robot can recognize its position in terms of locations. Through the use of algorithms, such as a cartographer by Google, mapping and location can be carried out, although other odometry sources, such as encoders, are generally needed. For cartographer, the use of a LiDAR, which it is capable of doing both, is enough, and together with an algorithm such as Depth Planner, is enough to comply with the target. For the conclusions, we have defined that the design of a mobile robot through simulations make it easier for designers to test and analyze various scenarios with different levels of complexity, starting from an initial scenario and robot, which leads to multiple cost savings compared to a physical implementation. The mathematics and architecture behind a robot can become quite complex, depending on the needs that need to be covered, and in turn on the environment which said robot will be involved. The design and implementation of a robot must always consider the well-being of living beings, with which said robot will be surrounded, either directly or indirectly, and it is the responsibility of the professional or the group of professionals to ensure this when they're designing the robot. And finally, our recommendations are that for a mobile base with a robotic arm, there may be cases in which the entire robot cannot be completely moved due to space restrictions. For these cases, the use of omnidirectional tires should be considered so that the robot is holonomic. Although the use of a LiDAR is enough for navigation, not all mapping and location algorithms use only LiDAR, but also necessarily require odometry, so it may be necessary to use encoders or sensors for tracking, such as the T265 camera from Intel. If in the future the use of inverse kinematics of the robotic arm is to be carried out from scratch, the use of pure revolutionary joints is recommended to reduce the difficulty of mathematical expressions. Thanks.